All right, recorded is rolling. Welcome to Friday, September 1st. So, for video context, in case you watch this video at home, my projector is not working today. So, yeah, I got a couple activities lined up, but yeah, I'll be working on the whiteboard in class. So, I'm trying to work for two different audiences here. Can make this work. All right. So, first thing, you guys got rollers on your desk, right? You guys always got rollers on your desk, right? You can make axes, straight lines, measure things. Okay? I'm gonna have you guys do an activity where you can use this ruler. This will be your measuring tool to be able to determine what is your reaction time. What do you guys think the setup is going to be for this experiment? You're going to use this. This is your only measuring tool. You're going to somehow determine time with a ruler, your reaction time. How do you think you're going to do that? Okay, so something to do with the distance change. Reaction time. How can you get reaction time just with a ruler?
Going to use the percent x equals b naught times t plus 1/2 at squared.
Yes. All right. Okay, you caught on that. So you guys remember these kinematic formulas, right? If you're sitting in my classroom, talking about this poster right up here, right? Right. By the way, are you guys memorizing these three equations? You guys know these equations are gonna like jump over and over and over, right? I highly recommend you memorize them. We're not gonna uh, force test you, but yeah, but high recommendation. All right. So say if you want to somehow get something with time, like a reaction time, and you have a tool that measures distance, yeah, there's only one equation that would get you there, and yeah, exactly what Steve said. It's gotta be the first one because that x has something to do with distance, and there's something to do with t time. Now the second one, why would the second one not be applicable to this? Yeah, nothing to do with distance, and the ruler would measure distance, so it's that one's kind of out. Right? Wait, what would be wrong with the third one? Yeah, nothing to do with time, right? Okay, so we kind of honed on. It's something to do with the first equation. Now, what's the experimental setup going to be? How are you going to use this ruler to figure out reaction time? What do you think?
Well, you're going to use the distance, and you're going to use the distance paired with the gravity constant.
Gravity constant.
Figure out time taken for it to travel that distance.
Aha. All right, I think you're onto this. All right, so here's what stuff's gonna be. We have you guys get into like chairs or just find some partners, and one of you is gonna hold the ruler like this, right? The other is gonna have their hand here, right? Now, my hands are two different people, right? You got like Alan and Bob. You get to see Alan here and Bob here, right? Okay. So maybe Alan drops the ruler and Bob catches it as fast as he can, right? And whatever centimeter mark you catch it at, right? Let's say you catch it at like let's go like 21 centimeters. I caught it like 21 centimeters. Okay? Isn't that going to correspond to some exact reaction time? Okay? Now remember, this only works if here. Do you want your fingers to be like way down here, but below the ruler? No, because then it's falling and you haven't captured all its yet. You want to hold it like right in the middle? No, because it's the same problem. Here. If you started at the zero mark, right, then wherever you catch it is a measure of like how far the ruler is falling. Right? So yeah, so we're looking at. You're right. This first kinematic equation. Now we can modify this. We can simplify a little bit. How can you simplify this? This first one. How can you simplify that? Because if you drop the ruler, what's the initial?
You should have the initial velocity.
Exactly. If you just drop the ruler, initial velocity 0. So that turns into x equals 1/2 at squared. Hey, is that the college equation? Is that college? Right? X equals 1/2 at squared. Okay. No, I might say, oh here, I got it right here. H equals 1/2 gt squared. That's the same idea, right? So H is a special kind of displacement. I can just call it like height or height change. G, gravity field, is a special kind of acceleration. That's just due to gravity, the gravity field, right? And you're solving for this time. Now, the way Paul Hewitt took you through the story of like this college equation is said, well, if you know something's been falling for some amount of time, you can calculate how far it fell. It's about 125 meters. You guys remember that for 5 seconds? Okay. But you guys are doing the reverse. Can you guys do the algebra and solve for time in terms of drop height and gravity field? Do you guys do that? All right. Do you guys think that you could figure out your reaction time just based on what I told you so far? All right, so I'm gonna go ahead and give you guys a minute, and yeah, go ahead and try it with each other. So drop some rulers, calculate your reaction times. All right, let me time. I'm gonna pause this video. All right, who wants to volunteer? What's your reaction time? Yep, what you got?
We got 1.7.
Or, okay, were you guys getting something like that too, about 1 or 2 seconds? Because if you did, that, guys, whenever you get an answer, especially in physics, it's a good idea to take a step back and say, does this number make sense? Do you think, because right now, guys, whatever's going on in the real world and our perceptions in our individual minds, like there's a delay, right? You're driving down I-95 and deer steps out in front of you. It's gonna take some time for your brain to react to step from the gas to the brakes, right? Okay. Do you think that time is about 1.5 or 2 seconds? Or does that sound too what? That sounds, I think way too slow, right? I think your reaction time, like the mismatch between what's going on in the world and our individual perceptions is probably like a fraction of a second, right? Right? And there definitely is a measurable delay there. But it would be like a full second. So if you're getting something that's like 1 or 2 seconds, what do you think? What do you think happened to the calculation that led you to get like such a ridiculously large number? Huh? How about this? Guys, what number are you using for G? 10 what? Meters per second squared? Oh, okay, yeah. You guys catch it on? And H would be in. Yes, if you need meters per second for G, then what are you plugging for H? Centimeters or meters? You gotta do meters, right? So if you caught it at the 21 centimeter mark, do you want to put 21 in for H? No, because guys, if you put in 21 for H, what you're saying is that 21 of these meter sticks just went through your hand. You're like, whoa. You're waiting for like 21 of these. No. You don't want to do 21. You want to do what? 0.21, right? Okay.
What about making, what about turning 10 meters per second to 1,000 centimeters?
That's the other way you can do that too, right? And that would also get you a correct answer. Yeah, you could leave the height change in centimeters. True. Right? You could change G to like about 1,000 centimeters per second squared. That would also work. Yeah. So you could go either way. Right? It's a outside the box thinking there. Right. So how about now? What do you guys get for reaction time?
20 seconds.
Yeah, about that sounds really fast. You catch about the 5 centimeter mark or something?
13.
Oh, all right. Yeah, so the average human reaction time is about a quarter to a fifth of a second, so 0.25 seconds, somewhere there. Right. So it's usually what people get for that. Right. All right. So you guys good on yeah, there we go. Go to that one. All right, guys, switch over to something else here.